Okay, so what's up, everyone? Good morning, good evening, depending on when you're viewing this. So, welcome to Fluid Flow 2. So, we'll discuss the more calculation related concepts related to the flow of fluid and mostly the energy requirements. Before we continue, as part of our visualization, I'd like you to visualize streamlines. So imagine if a fluid is flowing through a pipe or maybe a river, that each molecule will follow a certain path that varies slightly depending on the shape of, well, where the water is flowing. But again, there's a direction where movement flows along the line. Next is the continuity equation. So if we're assuming we're handling liquids, and because these are non-compressible technically, if there is a change in the diameter of the pipe, there will be a change in the velocity at that specific point. Because, for example, here the cross-sectional area is narrower as opposed to here, but the mass flow rate would remain the same, and that is governed by this equation wherein the density multiplied by the area and the velocity at one point is equal to the product of the aforementioned factors in the other. So actually, even if you had a slightly compressible, let's say gas flowing through, or slightly compressible liquid, if that's possible, then you'd still follow this equation. But the point is that throughout the pipe, the mass flow rate is the same regardless of whether um, it's a narrow portion or a wide portion of the pipe. Okay, as you've seen in equipment design, there are times wherein the pipe constricts or widens. But what's important is the mass flow rate either way should be the same. And to adjust for that, if there is a decrease in area, there will be an increase in velocity. So you can imagine this na parang pag yung garden hose, kino-constrict mo yung size ng butas, bibilis yung labas ng tubig doon, magiging water jet siya imbes na parang yung normal na labas lang ng tubig. Okay, so for this problem, it's simple and a bit straightforward. You could exercise your unit conversion muscles as well. So we're given a volumetric flow rate. This is a lot of beer at 1.8 liters per second. And the inside diameter of the pipe is slightly greater than 1 inch. And the density is slightly higher than that of water because of the presence of dissolved solids. So what would be the average velocity of the beer and the mass flow rate in kilograms per second? So although we do have this equation, take note that you want to find this and this. But you are given volumetric flow rate. So we know that the volumetric flow rate is related to velocity by dividing it by the cross-sectional area, which you could obtain from the inside diameter. So take note when calculating your area from your diameter, um, we should differentiate between diameter and radius, since usually the formulas we know for area are in radius, which is in this case pi r squared or pi d squared over 4. So please be careful when using that. And then once you get to solve um, the velocity, you can input um, I can calculate the area and input the other parameters to get the mass flow rate. And you could do the same if the pipe is substituted to one that is a half a diameter in size. Of course, with a smaller diameter, you would expect a much faster velocity at the same mass or volumetric flow rate. So remember at the start of FS15 we discussed dimensionless quantities, one of them being the Reynolds number. So this is not an apostrophe S because Reynolds is again the surname of the person who was able to popularize or quantify this thing. So it's a dimensionless quantity describing the flow characteristic of a fluid. So even though you use dimensions to calculate the final number, doesn't make sense if you attach the dimensions to it. But what it's simply stating is that depending on how fast the water flows and a number of other factors, you could tell if its flow rate is laminar or turbulent or transitory. So laminar flow is, imagine a faucet na pag binuksan mo yung gripo, tapos hindi mo alam, parang pag tinitigan mo siya, parang hindi siya gumagalaw, pero alam mong nagfa-flow siya. Okay, yun, parang walang masyadong disruption. On the other hand, turbulent flow is yung parang rumaragas ang river, complete with bubbles. And basically the motion, if you're looking at the streamline sa laminar flow, medyo parallel din dun sa direction ng pipe yung streamline. So pag turbulent, if you follow each molecule, medyo garalgal yung paggalaw niya. Okay, there's an example on the next slide. So there, as you can see, at different increasing Reynolds numbers, colored dyes on a flowing liquid, kung ano yung itsura, no? So there's a cutoff, of course, kung kailan nagiging turbulent yung flow. So the leftmost side is laminar, and these ones on the right are increasing levels of turbulence, and of course the ones near the middle are the transitory flow. Technically, the Reynolds number is the ratio of the inertial versus the viscous forces. And it's categorized as either laminar at less than 2100, yung compute niya na value, transitory or transition flow if it's between 2100 and 4000, and turbulent flow if greater than 4000. Ano bang importance ito? Depending on whether the Reynolds number is laminar or turbulent, nagbabago yung ibang equations or yung pagtrato natin sa isang fluid flow system. So, yun lang naman yung importance nun. And of course, it gives us an idea ano yung itsura ng flow niya. Okay, and since it's the ratio of inertial and viscous forces, what are the factors affecting this? So obviously, yung viscous forces would be viscosity. The higher the viscosity, the lower the Reynolds number. The inertial forces are determined by the density. So pound for pound, for a certain volume, how much weight ang pwede siya magkaroon, the velocity of the flowing fluid, and the pipe diameter. Okay. However, since mass flow rate is equal to density multiplied by the area and the velocity, we can rearrange Reynolds number to be a function of the mass flow rate, since sometimes it's much easier na timbangin mo kung gaano karami yung lumalabas dun sa pipe, no? And we have this form of the equation. Reynolds number equals 4 times the mass flow rate divided by the viscosity, pi, and the diameter of the pipe. Right here, I want you to first understand the problem carefully. So for example, if we have a 3 cm diameter pipe where the liquid is coming out of, and you want to fill a tank 3 meters in height and 1.5 meters in diameter, and you are given that the hypothetical, well, presumably liquid food, has the following viscosity and density values, what would be how long will it take if you want to fill it at the minimum, using laminar flow only, minimum fill time for laminar flow, and the maximum fill time at turbulent flow. So first, we have to understand that minimum fill time is yung pinakamabilis na laminar pa rin siya and pinakamabagal na turbulent flow na pwede mong gamitin. So, pinakamabilis na laminar pa rin would be a Reynolds number at the border, which is 2100. And yung pinakamabagal na turbulent flow would be a Reynolds number of 4000. So, you equate those Reynolds numbers respectively. So, either for number 1, ilagay mo to as 2100. Number 2, ilagay mo to as 4000. Okay, and interested ka sa fill time, which is makukuha mo pag nakuha mo yung mass flow rate. So based on the Reynolds number, you already have the viscosity, and you um, can compute for the mass flow rate as well because you have the density. So you get the mass flow rate, and from that mass flow rate, ibangga mo siya dito sa capacity ng tank, either mass or volumetric capacity. So, gaano katagal mo bago mapuno yung tangke kung ganito yung mass or volumetric flow rate mo based on that Reynolds number. So I think this is somewhat basic na calculation lang. So again, just plug in the equations, compute for the mass or volumetric capacity of this tank, and using the mass flow rate, you can get the time required to fill that. And again, you're supposed to get these answers, no? If you solve for minimum time at laminar and maximum time at turbulent flow. So obviously, a turbulent flow would have a corresponding much higher technically na flow rate compared to laminar in that case. Alright, suppose you have a transition from a tank to a pipe if you're gonna zoom in on this area. So this region where nagta-transition yung flow properties ng fluid mo is called the entrance region. So it's the length of the pipe where papasok siya with the whatever profile it had from the tank or the uniform flat velocity profile until it gets that fully developed flow na ito na yung itsura ng fluid mo. No, kasi sabihin natin, if you remember correctly, the fluid flow in the pipe is actually pinakamabilis yun sa gitna and halos zero yung nakadikit sa pipe walls, no? And that is why we consider the average velocity kasi dun sa loob ng pipe mismo, iba-iba yung velocity ng molecules. Pero overall, sa macro scale, may average velocity ka which you can use for computing yung flow rates mo for whatever purpose it may serve. So the entrance region in this case is dependent on the Reynolds number. So are most of our other calculations for fluid flow, as you can see here, and it's dependent on whether it's laminar or turbulent, and it's also dependent on the pipe diameter. So obviously, you would want to consider this entrance region kasi kapag gumawa ka ng pipe na mas maikli sa required entrance region, of course, you would come up with a transition flow pag lumabas yung fluid dun sa pipe, which may not be desirable. May bumubulwak-bulwak na flow, parang pag nagbukas ka ng grivo minsan, di ba, na sobrang lakas tapos tumatalsik everywhere yung liquid mo. So, of course, these ones are pretty straightforward. You can do this sample problem. You just need to plug in the values over there. So again, when we talk about velocity profile, ito yung velocity ng, well, probably individual molecules as it passes along the pipe. And for fully developed flow in a horizontal pipe, the only factors affecting their velocity profile is the pressure and the viscous force. So pressure yung force na nagtutulak sa kanya along the pipe. And of course, the viscous forces would, kapag mas viscous, medyo mas patusok yung itsura ng curve mo. Okay. Gravitational effects are negligible because they are much weaker, yung downward pulling force. Okay. Lalo pag horizontal yung flow kasi parang sobrang mas malakas yung tulak along the horizon plus yung effect ng viscosity. Kaya uniform siya, kasi kung may gravitational effect yan, hindi uniform along the middle yan, medyo mas magdodroop ng konti, no? So again, still in fully developed flow, if pressure is force over area, then pressure multiplied by the cross-sectional area is equal to the force experienced by the fluid at point A. When you pass along a pipe length, however, you experience a drop in pressure delta P because of viscous forces as determined by, in this case, ito yung sigma 2 pi RL. Okay, since the viscous forces go against the direction of the flow, inhibiting kapag mas viscous yung ano mo, um, fluid mo, mas malaki yung pag-inhibit niya. So anyway, in fully developed flow, you have a steady state constant velocity and zero acceleration. So again, at fully developed flow, if the acceleration is zero and the velocity is constant, then that means the net force acting upon the fluid is zero, such that there would be no pressure drop. Kasi kung may pressure drop yan, habang hinihila siya nung viscosity ng pipe, darating sa point na magiging zero na yung velocity niya. Dahil pababa ng pababa, parang yung friction baga. Para kang nagpipreno hanggang sa tumigil siya. Pero hindi, it's like a car cruising at constant speed, no? So yung ini-input mo na rate of power to move the fluid at yung kinokontra sa kanya ay equal lang so that it maintains that constant velocity. Okay, suppose we want to know the point velocities of the fluid at any point in the pipe. So we know that there's a maximum velocity at the center. Okay, so meron tayong average velocity, maximum velocity, and velocity at any point in the pipe, no? So again, max velocity is simply gaano kabilis yung tubig na nasa pinakagitna ng pipe, and it's given by delta P, or pressure drop, multiplied by pipe radius squared over 4 viscosity times the pipe length. Okay, on the other hand, velocity at any point, a small letter r radius away from the center of the pipe, is calculated using this equation. So we've skipped through the derivative process of how they arrived at these equations from the earlier velocity profiles, but if you want to, you could look at the Singen-Heldman on this one. But what's important here is that for the volumetric flow rate as a function of pressure drop across a pipe length, we can use this equation where delta P is the pressure drop and L is the overall pipe length. Mu is the viscosity and R is the radius, internal radius or inner radius of the pipe. And of course, the mean velocity across the pipe is given by the volumetric flow rate over pi r squared. Now, the velocity ratios for laminar flow is simply the maximum velocity at the center is twice of the average speed, while the for turbulent flow, the maximum velocity is 0.82. The average velocity over the max velocity is 0.82. For those of you na nag-Physics 70 series, hindi ko alam kung tatandaan niyo pa itong Bernoulli equation. Okay, but it's based on the law of conservation of energy. And it has three terms related to energy based on pressure, kinetic energy, and potential energy. So we can see here 1, 2, and 3. So it's basically saying that if there's a conservation of energy and negligible yung effects ng other forms of energy losses, then if you follow, let's say, a fluid through a pipe, then the sum of these should be constant. So first term is pressure. Kapag may pressure drop na pwedeng mabawasan ito. The second term is density velocity squared, parang 1/2 mv squared yung katumbas nito. So this is related to the kinetic energy. So pwedeng tumaas or bumaba yung kinetic energy either sa loss of pressure or kapag halimbawa nag-increase ka ng height. So in short, Kapag may isa sa mga terms na ito na tumaas, may isa na or more or dalawa na pwedeng bumaba and vice versa. Okay? And then this one, density times gravitational constant times z, which is the height value in distance terms, is related to your potential energy. So obviously, if you increase in height yung fluid mo, vertical pipe, halimbawa, mag-pump siya pataas, then tataas itong term na ito, but bababa yung kanyang kinetic energy unless you continuously supply um, energy through, let's say, a pump. Okay. So in this case, yung 1 and 2 na sinasabi dito, we could assume this to be different locations on the same streamline doon sa iyong pipe. We assume that the fluid is incompressible and flowing steadily. Although in this case, we assume that the fluid has close to zero viscosity, and therefore this does not account for viscous forces per se in its original form. Fluid does not do shaft work, parang wala siyang tineturn na um, let's say turbine para mabawasan yung energy niya at ma-transmit dun sa turbine, and that negligible yung heat exchange with surroundings such that not a significant amount of energy is being turned into heat as, let's say, friction or what, or simply because may thermal gradient yung fluid mo tsaka yung surroundings. So, ina-assume natin itong mga to when we're working with the Bernoulli equation. Alright, let's try this sample problem. You can solve it on your own. Suppose we have a 3-meter diameter stainless steel tank containing wine. That's a lot of wine, filled to a depth of 5 meters. Then at the bottom, you have a discharge port with a 10 centimeter diameter open to drain out the wine. Calculate the discharge velocity assuming the flow is steady and frictionless. So of course, point 1 is the top and point 2 is the bottom. So we only have to navigate through these 6 turns and assume that they're constant. So we equate these 3 to these 3. So to make our lives easier, thankfully in this illustration, both the top and bottom are vented to the atmosphere, and therefore the only pressure acting upon them is the atmospheric pressure. So since these two terms are equal, dahil parehas naman yung atmospheric pressure na nararamdaman nila sa taas at sa baba, equal to 1 atmosphere, then we cancel these two terms out, leaving us with just 4 terms. The potential energy terms, so may height ka naman, ang height dito sa baba ay essentially 0. Okay, kasi nasa bottom siya. And ang height mo dito sa taas is 5 meters. So for 1, if you have the density, then GZ1 mo na lang yan. Okay. And this one is automatically 0. So therefore, actually on this side, you only have one term, which is the one related to velocity. On the other hand, because the diameter of the pipe and the diameter of the tank is much larger in diameter ng tank, essentially in real life, halos zero, close to zero yung velocity nito. Kasi yung velocity nito is gaano kabilis bumaba yung height ng tanke dahil lumalabas yung fluid dito sa bottom. And because the difference in diameters is, 30 times, sobrang negligible ng velocity nito that you can consider this as 0. So that velocity 1 is 0. Actually, this is now just equating rho g z1 with 1/2 rho u squared. Therefore, if you cancel out the densities, you have now gz1 equals u squared over 2. So you can get the velocity by isolating U2 on one side. Okay. Okay, next is a siphon problem. So kung napapanood nyo yun sa mga palabas, di ba, yung parang di-drain out nila yung gasolina sa isang kotse. So ipa-prime nila, lalagyan ng gasolina yung isang tubo, tapos habang may laman yung gasolina yung tubo, i-shoot nila dun sa gas tank. And then magically, magfo-flow outward up the pipe, and out of the pipe yung gas galing dun sa gas tank. Kahit na parang uphill yung dinadaanan niya, so to speak. So, yun yung tinatawag natin na siphon na effect, no? So, for example, in this case, there's a 1.5 centimeter diameter tube siphoning water out of a tank, and the discharge end is 3 meters below the bottom of the tank. Okay, and the water level in the tank is 4 meters. So calculate the maximum height over, it's a very small hill, I presume, which the tube can siphon the water without cavitation, given that the temperature of the water is 30 degrees. So we're gonna still use this equation, okay? And yung cavitation, yan yung parang nagpo-form ng bubbles. Kasi nag-evaporate na yung water inside. And when that happens, of course, it can damage equipment because of the implosion ng bubbles. And at the same time, of course, it could impede the flow of your fluid. Alright, so to visualize, ganito yung itsura ng siphon setup natin, no? So we have the siphon tube there. It must be primed or already filled with the fluid that needs to be sucked, no? Kapag naglubog ka lang ng tubo dyan na walang laman kundi hangin, hindi gagana yung siphon mo. So kaya minsan, di ba, yung pag sa mga gasolina sa movies, sisip-sip muna sila dun sa tubo. Or may parang pump sila na ini-squeeze. But anyway, so here you can see there's the fluid. So we have 3 points here actually. The top of the fluid that's being siphoned out, the what do you call this? The maximum height of the siphon tube over the hypothetical hill, and the point kung saan lalabas yung fluid, which is lower than the point ng height ng fluid na pinagkukunan. Okay. So I put here the givens that we have. Point 1 and point 3 are both vented to the atmosphere, so the pressure term there is equal to the atmospheric pressure. Yung sa point 2 ay hindi, kasi iba yan dahil puno ng fluid yan. Okay. Then, because the diameter of the tank, it's much greater than the diameter of the pipe. Excuse me. So we could assume that the velocity, yung pagbaba ng height dito sa tanke, is 0, to simplify things. The velocity at point 2 and the velocity at point 3 are the same, simply because they're the same pipe diameter, no? Okay. The height at point 1 is 4 meters and the height at point 3 is -3 meters with respect to this horizontal level. So therefore, the height at point 2 will also be computed based on this horizontal flat surface as 0. Alright, so how do we solve this, no? So ayun nga, meron na tayong P1 equals P3 equals PATM. Okay. We could calculate the velocity at point 2 using this equation, which is also the velocity at point 3. Okay, by equating, no, yung mga terms natin. And then, so pwede mo na ma-solve yung U2 at U3 doon. And then, given tayo ng temperature na 30 degrees C, so to prevent cavitation, kasi cavitation happens nga, di ba, kapag nag-evaporate yung water natin. So dito, tabular value for the vapor pressure at 30 degrees C is 4.246 kilopascals. That means the pressure at point 2 must not um, exceed this value. So you could equate the pressure at point 2 at this value para ma-compute mo yung ito para ma-equate mo yung equation ng point 2 to any of the other equations. So kapag ginawa mo yon, you can now equate the Bernoulli equation at point 2 to either points 1 or point 3 so that you can get the unknown Z2 value, which should turn out to be 6.93 meters, which means this siphon setup will only work na 4 meters yung height ng fluid and then 3 meters below yung discharge kapag anywhere from here 4 to 6.93 meters yung maximum height ng siphon tube mo. Okay? Okay, energy requirements for fluid flow. So again, when we're looking at the fluid flow system, we assume that it is in steady state. So the flow rates are consistent, di pa bago-bago. The inlet and outlet fluid properties and conditions do not vary. If there is a rate of heat or shaft work, then they should be constant so that we could account for them. Okay. And then energy transfer is negligible from sources such as magnetism, electricity, and surface tension. Okay. So pretty much based din sa Bernoulli equation plus na yung pag-compute ng energy requirements. So saan ba natin ginagamit ito? So usually to determine, let's say, how big of a pump we need or how much pump power we need to transmit fluid over a line, whether it be yung water or if you're working with juices, ice cream mix or whatever. So engineers need to account for that, no? Na hindi ka lang basta-basta bibili ng itong pump na to, okay na to. So may compatibility yan, yung diameter ng pipe, yung size ng mga fittings, yung size ng pump. Hindi na natin naaralin yan, pero at least may idea tayo how much energy is needed to transport a certain amount of fluid across a certain pipe pump plumbing system to get to where it is, no? So I worked in the ice cream industry and wherever dun sa planta may makita kang network ng pipes kung saan nagta-travel yung ice cream mix mula dun sa batching or mixing room up until the aging tanks and up until the freezers, no? So yun talaga, depende yun kapag dinedesign mo yung planta, kailangan akma yung mga pump mo at the various locations and naka-strategize yun kasi hindi naman pwedeng shortest distance between 2 points lang parati yung pipe mo, kakanto yan kasi hindi naman pwedeng humarang sila yung iba sa may kisame pag dumadaan and so on para hindi nadadapa yung mga tao over pipes containing hot or cold fluid. Alright, if you look at the general energy requirements for fluid flow, parang Bernoulli equation lang siya na may dagdag. So, if you have a point 1 and point 2 na kailangan mo i-transmit halimbawa si fluid mo over a certain pipe system na tatago sa ganitong distance, sa akyat ng ganito, papasikot-sikot na ganon. So, yun yung kailangan mo i-consider. Ano ba yung mga factors dito? Pressure term. So, of course, there's pressure drops halimbawa throughout the system. We have to account for those, okay, and you have to counteract that pressure drop with a constant stream of work, mechanical work para maging constant yung velocity ng iyong pipe. Ito naman is the velocity, so if you're gonna increase the velocity of your pipe, of your fluid, from point 1 to point 2, like it's starting from 0, then of course meron ding work involved in doing so. And if you're gonna um, increase the height of your fluid, like you will pump it up a building, no, or towards a tank at the rooftop of your plant. So may factor din yun, may energy consumption yun. And then EF is for all frictional losses that are due to, let's say, how long the pipe is, kung may equipment dyan na nagkakos ng drops, um, or yung mga bends sa pipe mo kasi parang elbow macaroni siya, may 90-degree bend, may 180-degree bend, and so on. So kasama yun sa calculation, may factor yun, may effect yun. So we're just looking at basically the pressure energy, kinetic energy, potential energy, and frictional losses. Isa-sum up lang natin yun. It's just trying to account. So parang energy balance lang din, no? Yung mass and energy balance siya na how much energy will be needed to counteract each of these or to accomplish each of these points or energy requirements. Okay, so as I mentioned before, no, in each of these four terms, pressure energy is energy dissipation related to pressure changes from locations 1 to 2. Kinetic energy, change in velocity of the fluid. Average velocity itong tinitignan natin, take note ha. Okay. And then that depends actually, may alpha factor siya kung laminar or turbulent. So, pag laminar, ito lang yung equation mo kasi 2 alpha when alpha is 0.5 is 1. But when turbulent siya, may over 2 ka na factor dito. Okay. Potential energy, so overcoming change in height, and frictional losses are a combination of major and minor losses. So, mamaya i-break down natin yung EF, major EF, minor. So for major losses, there is what we call the small letter F for the friction factor. So it's used for major friction loss calculation. If you have a laminar system, then it's only 16 over the Reynolds number. Yun yung pinaka-multiplier mo. Otherwise, you have to use this log table. Okay. So, depende yan sa pipe material mo na may certain relative roughness, which is the epsilon value over the pipe diameter. Okay. And in this case here is the Reynolds number. Okay. So, how do you use this one? If you calculate the Reynolds number, pwede mo siyang tapos i-calculate mo rin yung relative roughness. Hanapin mo yung relative roughness curve kung saan siya nagfa-fall in. And then you just match that yung intersection ng relative roughness curve with the Reynolds number. And then i-project mo yung friction factor niya on the x-axis. But again, since it's a log table, yun lang, kailangan mong i-convert siya, no? Pero to make things easier, there is this table here is translated into this equation, no? So if it's a laminar flow, you just use this equation. If it's turbulent flow, you could use this equation instead para hindi na kayo mag-table-table dyan. Okay? So, major losses are losses due to the overall pipe length, no? Kasi usually naman sa isang pipe pump system, yung total length ng straight pipe yung mas marami kesa dun sa minor losses, which is yung pipe components like yung mga valve, T, no, kapag nagsisplit yung pipe into two streams or nagme-merge, elbows kapag lumiliko, and kapag nag-change ng pipe diameter, yung tinatawag nating contraction and expansion. So the major losses is given by this equation. So yung friction factor multiplied by U squared, the overall pipe length and the pipe diameter, which also translates to the pressure drop over density. Okay, and the minor losses ay yung summation ng contraction and expansion plus a summation of friction losses due to fittings. So lahat ito ay frictional energy losses. So sa minor losses, nandyan yung due to sudden contraction, which is the case with, for example, this one where from a tank to a pipe ay biglang lumiit. No? So meron kang energy loss dyan kasi nakikita nga natin bigla siyang nagkakaroon ng transition flow and may kung ano-anong kababalaghan nangyayari dyan. No? So simple lang naman when you have minor losses due to contraction, it's depende sa ratio ng cross-sectional area A2 over A1 kung anong equation yung gagamitin mo. If A2 over A1 is less than 0.715, you use this. And if it's greater than, you use this. Okay. Then if there is a sudden case wherein a pipe is connected to a large reservoir such as a tank, such that the A2 over A1 is roughly 0, then the CFC is automatically equal to 0.5. So pag nag-expand naman, nag-reverse ka ng situation, ganun din na may energy losses ka pa rin due to friction. And in this case, the CFE mo is simply 1 minus the ratio of the areas where A1 is the smaller area and A2 is the larger area. Energy losses due to pipe fittings is simply the summation of the losses from each fitting. So there's a chart for this in the next few slides. You just add up the individual CFFs to have the big CFF and then multiply it by U squared over 2. So ito lang yung example ng mga CFF. So ina-add up yan. So for example, if you have two long radius 90-degree threaded elbows, then that's 0.7 times 2. Tapos kung meron ka pang return bend na 180 degrees flange, then you add 0.2 to that. So you just sum each individual fitting and multiply the total CFF with the U squared over 2. So this one is just a throwback and a reminder that whenever you are dealing with problems in fluid flow, you always check first ano yung type ng pipe and then refer to this table for the internal diameter. Kasi sabihin sa'yo mamaya, a 1-inch nominal sanitary pipe, tapos bigla ka nag-assume ng 2.54 cm internal diameter when in fact, based on this table, it's 2.29 cm pala. Di mali ka na agad sa first step pa rin ng calculation mo. Okay? You have been warned. So in short, ito yung format niya, no? Overall. The difference would be whether it's in head format or yung energy requirement format. So kung mapapansin nyo dito sa EP, nagiging final na units natin is, or yung dimensions mo is V squared. So ang dimensions ito ay parang meter squared over second squared. But technically that doesn't make sense. But when you realize na kapag tinransform mo yon, it's actually similar to joules per kilogram. Okay, so para siyang how much energy per unit mass of the fluid, no, yung energy requirement. So i-multiply mo yun sa mass flow rate to get the power requirements in watts. Okay, yan, mass flow rate. There's also this format, yung head format na tinatawag natin. Notice meron siyang G sa ilalim, yung gravitational constant, which naman converts the final units to just the length dimension, puro meters. No, kasi yung pump head na pag-uusapan natin later on, yun naman ay nakabase sa yung simplification na parang gaano kataas ang katumbas nito na itong energy na to, gaano kataas na height ang kaya niyang iba to yung fluid, parang ganon. Yun kasi yung pump head terminologies.